All right, so last time I tried to convince you that representation theoretic structures provide a tool to construct meaningful and analyzable probabilistic objects. And I tried to demonstrate how representations of symmetric and unitary groups, so in other words, Schur functions, can be used to construct a two-dimensional growth model that in various projections give random matrix type models and also exclusion processes. What I want to do today is to use the same approach, but for a more sophisticated algebraic structure. What I'll be talking about is very recent work. Parts of it are published in 3 preprints by now. These are the authors. All of them are recent. They are within 6 months from today. So the general title for what I'm going to talk about is McDonald processes. And given that yesterday I talked about Schur processes, the mic up. Can you turn the mic up? Is it better? No? Hello? 1, 2, 3. Can the last row hear me? Okay, thank you. All right. So the general title is McDonald processes. So the whole thing is based on, rather than Schur functions, on McDonald symmetric functions. McDonald symmetric functions are a remarkable object. They were discovered by McDonald in mid-80s and almost by accident, I guess. And I'll tell you a little bit about them. So it's easier to talk about McDonald polynomials. McDonald symmetric functions, as usual, will come from the stability property of McDonald polynomials. When the last variable is set to 0, then we go to fewer variables. So McDonald polynomials, p lambda of x1 through xn. If I only use n variables, then lambda is a partition with at most n rows, or better to say just an n tuple of non-negative integers. So these are symmetric polynomials in x1 through xn. Oops, one parenthesis. In x1 through xn. So this is the notation means that these are symmetric polynomials in x1 through xn with coefficients that are rational functions in 2 parameters q and t. Q and t can be viewed as formal parameters. It can also be viewed as numbers between 0 and 1. If one wants to use some sort of positivity, you need actual values, and that's what I'm going to use. The connection to the previous talk is achieved by the relation that if I set the 2 parameters to be equal, then the McDonald polynomials turn into Schur polynomials. But there is much more involved. If one takes McDonald polynomials, sets t equal to q to the power beta over 2, I guess that's the usual notation, and then send both to 1, then the McDonald polynomials turn into what's called Jack polynomials, which are eigenfunctions for the well-known Calogero-Sutherland integrable system on the circle, with beta serving as a coupling constant. And there is one more degeneration. Well, actually 2 more. If I take p lambda and I set q to 0, and these are also, they have been known long before McDonald work. They're called Hall-Littlewood polynomials, and one representation theoretic interpretation of them is as spherical functions in representation theory of GL over p-adic fields. If I take p lambda and set t to 0, then these end up being something called Q-Whittaker functions. And I'll talk about them a little later. They have interpretation and representation theory of quantum GL. So the point is that Macdonald polynomials somehow unite a few remarkable families of symmetric functions, but themselves they do not admit an easy definition. So let me try to give two definitions actually. None of them is direct. There are no explicit formulas for well, there are some formulas, but they can't really be called that explicit. I can't write a determinant as in the short case to define them. So let me give a formal definition. So first, on the algebra of symmetric functions, one introduces a dot product. Again, you should always think about the simpler case. When q is equal to t, then whatever I say can be interpreted in terms of sure functions, with which I hope by now you are familiar. So the dot product is defined on the basis of, so these are little p's and little p's. So the little p is the basis of the power sums. When I index it by partition, I just take the product of power sums with the parts being the partitions. So this basis is orthogonal, but then there is a non-trivial dot product on the basis. The norm is not 1, but is given by a certain expression. Okay. So this part depends on q and t. When q is equal to t, this goes into 1. What's mi? So mi is the multiplicity of I in lambda. Okay. So the partition has some number of 1s, some number of 2s, and so on, and m1, m2, and so on are the multiplicities of those. Sorry, I didn't hear you. Can you repeat? Yeah, you are right. Thank you very much. This is supposed to be J. Yes. All right. So then one takes the basis of monomial symmetric functions. So these are monomial symmetric functions, which is just taking a monomial x1 to the power lambda 1, x2 to the power lambda 2, and so on, and symmetrizing over all possible permutations. And then one applies the Gram-Schmidt to it. And that gives a basis. Now, Gram-Schmidt should be applied when there is a certain order on the basis. So the order Gram-Schmidt with that lexicographic order on partitions, that produces a basis. And that basis is the basis of Macdonald polynomials. It's a definition that falls from the sky. It's not clear. It's a good definition. Gram-Schmidt is very non-explicit. And what good does it do? Now, here is a definition number 2, which is much more structural. If one looks at the following difference operator on functions in n variables, and this is the sum, I goes from 1 to n, product j not equal to I, txi minus xj, xi minus xj, f of x1, q, x, I, and then the other ones are unchanged. So this is the first order q difference operator. This is one variable being multiplied by q. This is a certain rational prefactor. Now it turns out that this operator, so this operator d1 preserves the space of symmetric polynomials in X's, which is not very obvious, but not hard to check, even though there are denominators here. And moreover, it diagonalizes, so d1 diagonalizes with simple spectrum. And d1, if I denote the eigenfunctions by p lambda, then the eigenvalues are actually not hard to write down. Okay, so I guess the first statement is that eigenbasis is parametrized by partitions with at most n parts. And then This is the eigenvalue that depends on t, on q and t. And the eigenfunctions are called Macdonald polynomials. It's immediately visible that when q and t are generic, these numbers are going to be distinct. And so this actually completely defines, well, up to a constant, the Macdonald polynomials. This definition actually fails in the case of Schur functions or any other degeneration because the eigenvalues get clustered together. They got glued. And so this doesn't define the basis. But in the Macdonald case, this is enough to give a complete definition. This actually shows that in some respects, Macdonald polynomials are simpler than in other ones. For example, there is a Fourier transform in them. There is a certain symmetry between the index and the argument that's also not present in either of the degenerations. So in some sense, this is the canonical object. And yet, giving a representation theoretic definition of it is difficult. What happened is that the theory of Macdonald polynomials gave rise to a new branch of representation theory that sometimes, I guess, people now refer to as representations of double affine Hecke algebras. I'm not going to go into that at all. I'm just trying to emphasize that although non-explicit, these are fairly remarkable objects. Okay, so what I'm about to say is that all the ingredients that I needed to construct probabilistic objects from Schur functions, the Cauchy identity, this Q Cauchy identity, these Q functions, they're all there for the Macdonald polynomials. So the Cauchy identity has the following form. Let me write, so here is a piece of notation. Q lambda is going to be P lambda divided by P lambda, P lambda. So this is the dual basis. Right? In the case of the Schur functions, this quantity is 1, and so Q and P is the same. Now Q and P are the same polynomials, different by a constant. So if I write what's called the reproducing kernel, if I sum over all lambda, then there is a nice product formula, which is what? The product over all ij, txi yj semicolon q infinity divided by xi yj q infinity, where I use the notation of the q symbol. So a semicolon q n is 1 minus a blah 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 1 minus a to the power q n minus 1, the product over geometric progression, and aq infinity is the infinite product of this form. So this is the Cauchy identity. There is also, there is also a skew Macdonald polynomials that are defined in the same way, using the crop product. One takes Macdonald polynomials, restricts them to fewer variables, and then decomposes into a basis of fewer variables. That gives coefficients, which is skew Macdonald polynomials.
Excuse me,
yeah.
About the notation. Haven't P lambda be defined to be orthonormal just on the line above?
P lambda, which one? This line?
You're right there. P lambda are orthonormal basis, Gram-Schmidt to everything.
Gram-Schmidt gives orthogonal basis, not an orthonormal. So it depends on what you mean by Gram-Schmidt. If I just subtract lower terms, it's not going to change the norm. I don't divide by the norm. So the highest coefficient of P lambda is M lambda. Okay? Yeah, that's the reason I need the norm. I mean, you can divide by the norm there, but then you'll have to reintroduce it here. So if you wish, you can write it in a coordinate sort of independent of the Gram-Schmidt procedure in that way. Okay. All right. And so then I can define the Macdonald measures. Macdonald measures, which is the probability of lambda is P lambda of x, Q lambda of y divided by the product, well, by the partition function. So let me call it z. So this is z. And then I will also define right away the Macdonald processes. So Macdonald processes, they will be similar. I will just do the special case. They will be similar to the Schur processes that I talked about. The schematic picture will be this. That's something I used yesterday. And so the probability on a sequence of partitions lambda 1 through lambda n will be the product of skew functions for these arrows, skew McDonald functions for these arrows. So the skew functions I will also denote by p and q. They're different by a constant. So this is p lambda 1 in some variable a1, p lambda 1 over lambda 2, a2, blah, 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 p lambda n over lambda n minus 1 of an. So there are parameters a1 through an. And then the final factor corresponds to this arrow going down. Rho is a specialization of the algebra of symmetric functions, q lambda n of rho. Now immediately the question arises whether McDonald polynomials take non-negative values. What are the non-negative specializations of McDonald polynomials? That's a very meaningful question. There is a conjecture on that, which is, so the conjecture is that non-negative specializations, McDonald non-negative specializations of lambda are characterized by the fact that if I take the generating function of q's on one row partition, let's say with n here, so the sum n greater to or equal to 0, evaluated at rho times z to the power n, then this should have the form e to the power gamma z, product 1 plus beta I times z, 1 alpha I z semicolon q. Actually, I'm lying a little. T alpha I z q infinity. That just comes from Cauchy identity, and then there is an extra factor with betas. Okay. You may compare it with the Drey-Thomas theorems that I formulated last time. It's not hard to prove using known properties that when q and t, so I'm always assuming that my parameters q and t are between 0 and 1. So it's not hard to prove that specializations defined by this identity are non-negative, but the exhaustion is very difficult. So nobody knows how to prove that there are no other non-negative specializations. This statement is known under the name of Karov's conjecture, and it's almost, I guess, 30 years old. So if anybody knows how to prove it, that would be exciting. All right, so this row here is a non-negative specialization, which I will actually take well, I guess in the next 5 minutes, I'll just take it to be the one defined with this factor. So these things will disappear. And then, so then, as yesterday, this defines a measure on sequences of partitions that increase. If I can draw these partitions by their coordinates slightly shifted, that produces for me a triangular array of particles. So the kth row in this array consists of the particles which are the parts of the kth partition shifted by j, I guess. Yeah. Again, similarly to what I was doing yesterday, I can define a Markov dynamics on these arrays. So for that, I need certain transition probabilities that go down from level k to level k minus 1. I also need evolutions in time along each row. I need these to commute with those. And if that happens, I can apply the general construction I talked about yesterday to define the evolution on the whole array. So just to sort of, if you don't remember certain formulas from yesterday, I'll write the form of the links that go down and of the time evolution. So going down from level k to k minus 1, if I want to write the stochastic matrix, then it has the form I need to conjugate P lambda k minus 1 of A1 A k minus 1 over P. So this is the conjugation by something like Vandermonde determinant in the simplest situation. This is being multiplied by this Q function in a single variable AK. So these are the links that go from level n down by 1. And then the probability is the time evolution. So the probability, if I go from lambda k, I don't know, time, no, I don't want to use t naught. Well, let me use tau naught. If I want to go lambda k at tau 1, then this probability will also have a similar form. There will be a conjugation by, actually there will be a conjugation by also p's, right? So p lambda k at tau 1 over p lambda k at tau 0 at A1 through AK, A1 through AK, and again there will be a skew function here. So these are really similar. They are exactly the same. There will be a specialization. They're exactly the same as the ones I used for the Schur functions. They are similar to each other, and the fact that they commute follows from the skew-Cauchy identity, or the MacDonald analog of the skew-Cauchy identity. All right, so what I'm trying to say here is that the whole construction mechanism carries over from the Schur case to the MacDonald case with fewer differences. Now, the object that one gets, of course, is different. Now, maybe I could ask to turn on the projector. I'll need it in 5 minutes. Let me meanwhile tell you what kind of Markov chain one gets. So in what follows, I'm going to set t equal to 0. So I have two parameters in the MacDonald processes, q and t. I'm going to kill one of them. Okay, it makes things simpler. And then here is a definition, or rather not the definition, but the result of the evolution on the triangular array. Remember, yesterday the evolution was that the particles were jumping to the right, and then they were blocking and pushing each other, right? So there was a part, the Schur case, there was a thick boss at the bottom, then these were fewer. These were weaker bosses and so on. Now, so I'm claiming can I have the light on before I do it? Thank you. So then I'm claiming that the construction that I just mentioned with the MacDonald polynomials gives the following evolution on the triangular array of particles. The jump rate of a particle will depend on its neighbors. Okay, there will be no blocking and pushing here. So if this is a particle, so this is a triangular array. The particles must interlace. So the jump rate of this particle, this whole thing is inside a large array, right? So the jump rate of this particle will depend on 3 of its neighbors. Okay? I want to emphasize I'm not inventing anything. I'm just using the scheme with MacDonald polynomials to produce the dynamics. And I'm telling you what happens. This is a manipulation with formulas, right? So the rate of this particle is equal to, let me call these distances something, A, B, and C. This is equal to 1 minus q to the power A, 1 minus q to the power B, and divided by 1 minus q to the power C. Now what's good about this thing? Well, this rate is local. It only depends on the configuration in the neighborhood of my particle. That makes the problem somehow physical. One can try to employ various principles to describe what will happen. But other than that, You get a picture like, you get these rates. How do you know what this measure is doing at large times? So I'll try to, and the reason I asked for the projector is to try to play into a discovery game. Now, of course, the most interesting part of the picture is skewed, so let me do that. So this is a simulation here that was written by Patrick Ferrari that takes this evolution on the triangular array and runs it on a computer. Okay. So let's just see what happens. Now, one thing I'm doing, I'm taking Q to be close to 1. Now, why am I doing that? Well, that's because if Q is not close to 1, then these powers of Q decay quickly when A, B, and C get large, and the interaction is too local. Somehow, the asymptotic behavior of any local model is described by the universality class. So when Q is not going to 1, we expect to see the same behaviors in the sure case, which is Q equal to 0. So the sure, since T is 0, Q equals 0 is the sure case. So that's when all these things are 1. So if Q goes to 1, then maybe something different happens. So Q here is 0.99. And OK, so let me click on start. Well, this is how it looks, OK? So you have the blue particles, and they just run according to some rates. I realize this is not a very illuminating picture. But I can do the diffusive scaling. So I can subtract the time and divide by the root of time. Let me reset. Rescale. So this is my starting configuration. It's densely packed. And then it starts running. Now, this is a more interesting picture. I hope you agree. And what you see, the particles, well, they do fluctuate, of course, but they have some sort of a deterministic structure behind, right? Now, what's more interesting is that, well, OK, so you see the curves, right? So there are some curves appearing, right? Now, if we run the simulation for some time, which probably will take half the lecture, what you will see that these particles, as time gets large, will arrange themselves in a perfect lattice. Okay? See, this thing here, this is becoming a straight line. Okay, well, it already became kind of a straight line on the bottom 3 levels, but it will happen higher with a larger time as well. And so all these particles in the first approximation will sit on the perfect lattice. Okay? And then if you run time further, then this lattice will destroy itself. So it, again, will be somewhat random. Now, this is kind of an interesting behavior. And what I'll do next, I'll try to describe how McDonald functions help and what is behind this crystallization behavior. Okay? So this is all I wanted to show. I'm happy to show. I'll leave the simulation running. If at the end of the lecture you want to see what happened to the array, you're welcome. You'll see the lattice will get quite good. But then can you lift the whole thing up? Thank you. All right. So McDonald polynomials give you the object. You run it on a computer. You see the object is probably interesting. Now, how do you analyze the object? The first two, maybe the second and the third lecture that I gave, I showed you how to analyze sure measures. So sure measures were determinantal processes, and then you have analytic tools to deal with them. McDonald processes are not determinantal processes. And that was the major reason that nobody took the initiative of studying them, because the basic tool that allows you to say anything was lacking. Okay? However, it's actually not hard at all to come up with such a tool. So how to analyze McDonald processes? Well, here is the answer. It's kind of remarkably simple. Okay. Now this is the And then there is some product, okay, that I'm not going to do. Oh, well, maybe I should write down. So I have set my my t to 0, so now this is just this. Product over Lj. This is my identity for the partition function of the McDonald measure. So the process on the triangular array, on every line, this is a McDonald measure. So on every line, it has a form like that with various x's and y's. So maybe I should be putting here row 1 and row 2 or something like that. Now, the key line is here. What happens if I apply the first, this is called the first McDonald operator. What happens if I apply the first McDonald operator to both sides? I get D1. Well, these are if I apply in the variables x, right? These are the eigenfunctions for D1. So I can move it in and I can put here the eigenvalue, which I never denoted anything. So let me write d lambda here. Right? So then if I divide both sides by the partition function, then on the right I get d1 applied to this product divided by the product, kind of the logarithmic derivative except for discrete. And on the left I get the expectation of the observable that's equal to the eigenvalue d lambda on a partition. Right? Now the eigenvalues are still here. And so here are the eigenvalues. They're written here. Now if in these eigenvalues I'm going to set t to 0, then you can see in the eigenvalue the only thing that survives is the last term. So by this fairly innocent manipulation, I get myself a formula for the expectation of q raised to the power, which is the last row of my partition. Now this expectation is very explicit, because this is just some explicit product, and d1 is the operator written on the right-hand side. Now this object, the McDonald measure, is very inexplicit. The McDonald polynomials do not have an easy presentation. Okay? But who cares? So we have one observable for which we can compute expectation. Are there more? Well, there are some that align on the surface. I can apply powers of the first McDonald operator, and that will give me moments of this random variable, and this will amount to taking powers of the operator. Right? Now what's more, McDonald operator, so this is the first order operator. There are McDonald operators of any given order that are diagonalized by this basis. They're given by a very similar formula. I'll put it on the board. Oh, sorry. The sum is over all subsets J inside 1 through n. The number of elements in J is k. The product, or maybe I should put here I. So then there will be a product of I in I and J not in I. And then the same term here. So I'll put t to 0. So this is, or maybe I shouldn't put t to 0, because the formula is just the same. And then here I will have the qxi1, qxik. So I need to multiply by q variables whose indices are in this subset. Okay? So these are McDonald operators, a remarkable object. They are all diagonalized in this basis. The eigenvalues are elementary symmetric functions in this set. And in particular, when t is equal to 0, the eigenvalue is going to be q raised to the power lambda n plus lambda n minus 1 plus lambda n minus k plus 1. Now if I have many operators, each of them diagonalizes in this basis, I can play this trick with any of them. I can also play this trick with their products and their powers. What will happen is on the left-hand side, I will get expectations of products of the observables, which are products of the eigenvalues here. And on the right-hand side, I will get some fairly explicit expressions. Now that's already pretty good, because what happened is that I produced many, actually infinitely many observables on my measure. If I manage to analyze them asymptotically, that gives me some information about my measure. Let me do, or maybe write one concrete formula. At least one expectation. How does it look? So here is the formula. The expected value of q to the lambda n raised to the power k. Okay. And this is this is for the dynamics that I showed. So that, right. So this here, this particle here in the nth level, this is essentially lambda n. And so I'm writing the expectation of q raised to this position. So then this is equal to minus 1 to the k over 2 pi I to the k. And then there is a k-fold contour integral, product ZA minus ZB, ZA minus QZB, A less than B, product J from 1 to k. Now I forgot to say that that in this general construction I'm setting all my parameters equal to 1. You know, if I don't, then I need to put an extra factor here, which I don't want to do. So then this is 1 over 1 minus zj to the power n e the q minus 1 times tau zj. Tau is the time of my Markov chain. And this is dzj over zj. And then I need to say what the contours are, and the contours look like that. This is 1. There is a zk that goes around. I need to avoid the poles of this factor here. So I take a small circle around 1. Q is also, let's say, close to 1. So when I multiply it, I get something that's a little shifted. And so I take the second contour to be slightly larger, and then all of them be slightly larger.
Excuse me, do you understand correctly that all these formulas are on one horizontal level only? You don't have formulas for joint distributions on different horizontal levels?
We do, but that's unpublished.
But not on the board?
Not on the board, yes. Yeah.
So with respect to what measure this expectation?
Right. So this expectation is with respect to the measure. So the measure, the probability of lambda 1, lambda n is proportional to the product of Macdonald polynomial evaluated at 1, 1, a total of n ones, times the q lambda evaluated at a specialization rho, which is the Plancherel specialization. It corresponds to many variables which are small. Okay. All right. So then, again, as I said, well, you may not like contour integrals too much, but I hope I showed in my third lecture that when you have contour integrals, you have some freedom in deforming them and doing asymptotic analysis. And so let me tell you, let's see what I want to tell you.
Excuse me, what is tau here?
Tau is the time in the evolution. So this is rho tau. So this measure describes the nth row in the triangular array in the evolution that I showed after time tau. Okay? And then again, let me emphasize, this is just one formula, right? It corresponds to the power of the first Macdonald operator. One has many. All right, but in particular, this describes all moments of this random variable. And so, theoretically speaking, you can get the distribution of this last random variable. Now, why would you want to do that? Well, so the picture that I just erased, right? So I told you that the rate of jumps of this particle depends on 3 neighbors. Right? Now here is my triangular array. This is the particle for which I can compute something. Whose rate does it depend on? Well, if I draw that picture, I need to do that. But there are no particles outside of the array, so these dependencies don't exist. So the jump rate of this particle depends only on a single particle here. Now the conclusion is that the projection of my Markov chain, again, as in the Schur case, to the leftmost side of the triangle is Markovian. What is this evolution? And the evolution is the following. One has, so if I put it down, then I have a one-dimensional lattice, and I have particles sitting here, and the jump rate of each particle is equal, so the rate is equal to 1 minus q raised to the gap, where the gap is the number of empty spaces. So it's 1 here, it's 1 here, it's 0 here. This is a softened version of TASEP. So again, imagine there are cars on the freeway. They are going to approach the car in front if there is a gap. But the larger the gap is, the more is the probability that the driver will want to do that. This is sort of more realistic, right? You don't push the pedal until you're very close to the car in front, right? So this is, we call this thing Q-TASEP. Clearly for q equal to 0, this is just the usual TASEP, but this is something more. And so what that formula tells you, it tells you the moments for something related to particles, so that Q-TASEP started from some initial condition. All right, so then now let me tell you about some asymptotics. So what I want to do, I want to send my time to infinity, right? I also want to send q to 1, because if somehow I don't do that, I don't leave my universality class of KPZ. Even though the problem is different, I stay in the same universality class. Well, I have 2 parameters. I need to relate them somehow. In fact, the answer will depend on the way I relate them. You saw in the picture that first the particles live on some curves, and then the curves turn to a lattice, which I now see on the simulation. You can look at it later if you want. So what I'm going to do, I'm going to take q is q to the minus epsilon, and then I'll take tau of size 1 over epsilon squared. Now this is the regime in which this perfect lattice appeared. This is the crystallization regime. If I take tau to be smaller than this, then I get the curves picture. And if I take tau larger, then I actually converge to the random matrix picture. I get to the GUE minor process. These will behave as eigenvalues of random matrices. Well, you take the random matrix and you take its corners, then the eigenvalues arrange themselves in a triangular array, and that's what you get if you take time here to be larger. This is sort of the universal limit that you always get in dynamics like that if you run it for too long. I'm not going to run it for too long. I take this window where my lattice appears, and then the theorem is the following. Indeed, one proves that the particles arrange themselves in a perfect lattice. In the first approximation, actually in the second approximation. So the coordinate of this particle is going to be, in the first approximation, t over epsilon squared. This particle will be a t over epsilon squared plus log epsilon inverse over epsilon. The coordinate of this particle is going to be tau over epsilon squared plus twice log epsilon inverse over epsilon, and so on. So this will be the spread of the lattice. Okay? Now, there has to be some randomness that remains, right? The particles are still wiggling a little bit, so there will be a correction. So there will be fluctuations of size 1 over epsilon. Everywhere, and here as well. So I can write that lambda n is equal to t over epsilon squared minus n minus 1 log epsilon inverse over epsilon plus some fluctuation ln dependent on t divided by epsilon. Now this picture can be just read off from these formulas. It's fairly simple. Now the interesting question is, what are these fluctuations? Right? So I subtracted the underlying lattice, I get down to the fluctuations. Right? So this can be guessed. If you take the Q-TESAP evolution, that's written here, this one, and if you scale it in the way that I wrote here, the evolution will converge to a stochastic differential equation, which is going to be a simple one. But rather than doing the argument that everybody can do, I gave you everything, essentially everything. This is a fairly simple evolution. I told you what the scaling limit should be. If you scale that evolution, you'll read something. Instead of doing that, I'll give you the form of the solution for the stochastic differential equation in the Feynman-Katz representation. And that's going to be the following. E to the power ln will be distributed as the following object. As usual in Feynman-Katz formulas, this is going to be the integral over paths of something. So let me tell you what that is. So the integral is taken over paths, broken paths that go from the point 1, the port 0, 1, to the point t, n. So there are a total of n lines. The paths that go are, that's that color. These are the paths. So this is a simple situation when there are only, well, the space of paths is finite dimensional. So the S's that I have here are the jump locations for these paths. So this is S1, S2, up to Sn minus 1, up to Sn minus 1. And then as I go along the path, there is a Brownian motion on each of these lines. They are all independent. These are B's in my notation. What I do, I take the increment of that Brownian motion over the segment that I take on the paths. Right? So this here is the Brownian motion number 2 at the point S2 minus the Brownian motion at the point S1. Or if you prefer, you can write it as the integral of the derivative of the Brownian motion, which is white noise. Now we are back to the situation that I described in the first lecture. This is a directed polymer in random medium. There is a white noise on a union of lines. There are paths, and I'm integrating over all paths the energy that each path collects along the way, where the energy is E raised to the integral of the noise along the way. Now this is called, people usually direct, this is called semi-discrete Brownian polymer. For the first time it was introduced by O'Connell and Ure in 2001, and sometimes people call it O'Connell-Ure polymer. O'Connell and Ure observed some integrability properties of the polymer. And later on, O'Connell wrote a beautiful paper in 2009 where he identified the distribution of this O'Connell and Ure polymer with something that can be expressed through solutions, through eigenfunctions of the quantum Toda lattice. Okay? In fact, that paper served as a hint for the development of this work. And the reason the quantum total lattice arises is that in the limit that I describe, the Macdonald polynomials actually converge to what is usually called GLN Whittaker functions, which are eigenfunctions of the quantum total lattice. So they are eigenfunctions for the operator, which is the Laplacian plus minus twice the sum E xi plus 1 minus xi. I goes from 1 to n minus 1. So this is an operator on Rn. So they appear, in a sense, the appearance of the quantum total lattice in the polymer problem is the inheritance of the Macdonald structure we started from the very beginning with. Okay. All right, but so far this is all baby asymptotics. Okay. Because what happens is that so the n here is kept finite. So I'm always working on measures on finitely many particles. This is not the real results one wants to get to. Now, the real results one wants to get to, in both my original dynamics and in this situation, is when n gets to infinity. Okay? That's when these paths get really large. Okay? In that sense, in that limit, one expects to see either KP's universality, which now would be a very non-trivial statement, or the situation when this path actually approaches Brownian motion, and then one gets the fully continuous Brownian polymer, when this integral is the integral over paths of the Brownian bridge, and the partition function becomes the solution of the stochastic heat equation. Okay. How easy is it to get there? Well, it's not easy. The problem it's not easy is the following. We have very good formulas for the moments. So this formula actually translates itself into the expectation of e to the minus, this was supposed to be ln capital, e to the minus, or maybe e to the ln k, something like that. So we know everything about the moments. Now the problem here comes, this is sort of a very unpleasant realization, is that this is the situation when the moments don't do anything for you. The phenomenon that I referred to in the first lecture called intermittency says that there is a probabilistic reason why the moments are not going to work. The reason is that this distribution, well, if you take the exponential of a normal random variable, the moments grow far too fast to define it, because the large deviations start contributing too much into the moments. So the moments have no idea what the distribution is doing. It's not great. So this there is a story that flatters mathematicians that comes with it. So 2 years ago, when this subject was sort of gearing up, physicists also participate, clearly. And so they looked at the problem of the fully continuous Brownian polymer. So the integral is over the Brownian paths, and this is e to the power, the integral of the two-dimensional white noise along the path. Now there is something that I mentioned before, in the first lecture, that if I take this integral over the Brownian path, so the Brownian paths between 0, okay, let me just not write the integral, just do the picture. So here is 0, here is time t, then you have bridges, and then you integrate the two-dimensional white noise, and I call it zxt. So this is the integral over the Brownian path. So then if I take the expectation of z of x1t, blah, 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 z of xnt, actually you can take all x's to be the same, but it's into, so this is x1, x2, and so on. Then the moments are somehow not hard to compute. Well, not hard in quotation marks. So this happens to be a solution of the quantum many-body system called the delta Bose gas. And that can be solved by beta ansatz. So you get the moments. Then you plug in all x's to be the same. You get this for any k. And then you say, find, you know, the moments. What's the distribution? Well, what do you do? Right? So if you have a random variable, you can try to do its Laplace transform, and then you open it up. And then this is the sum of z to the k, c to the k, minus z to the k over k factorial. And then you hope that you move in the expectation here. And then you sum, and that's your answer. Well, the problem is that if you move the expectation here, in this problem, then the intermittency kicks in. And this thing behaves as e to the power k cubed. The series has no chance of converge. Well, that never deterred physicists from doing their work, right? So they take this series, and they do something to it. This is such arguments have a long tradition. They're called replica trick. This is some sort of an analytic continuation in an integer parameter that in this case is k. So they do the analytic continuation. They say, well, we know that, then we know it for any real k, and then you can really extract something. Well, the first time they did it wrong. And that's the flattering thought for mathematicians. Mathematicians later derived this expression. It was done by actually in two works, Amir, Corwin, and Castell, and then in parallel, Sasamoto and Spohn solved this problem using previous work of Tracy Whittam on asymmetric simple exclusion process. This is a parallel line of reasoning that so far has not intersected of what I was talking about. Essentially, that's a different way. This asymmetric simple exclusion process is an exclusion process when particles jump right and left. And it can be used to approximate the polymers, somewhat similar to the way that Q-TASEP can be used to approximate the polymers. But in any case, so what I was trying to say is that even though this replica trick doesn't do the job for the Brownian polymer, it can't. You know, it's not because you're not trying hard. It's because there are reasons. You know, the model is such that the moments are just not good enough. However, one can do this replica trick before going to the limit. It shouldn't really be called replica trick. See, I have these formulas here for the kth moment. And it just so happens that if I take the generating function for these moments, this is a Q generating function, and this is the Q analog of Laplace transform. So I'm really doing something like that. Okay? Now this is the Q factorial that sits here. Then these formulas, then the series has no problem. Sorry, there should be a sum. Okay, greater or equal to 0. The series has no problem in convergence. These guys are all between 0 and 1. Q is between 0 and 1. And so I take that formula. It can be manipulated. It's not a very trivial manipulation, but it's not too hard on it. And remarkably, there is a determinantal formula that arises in this way. Now, the reason that determinantal formula arises is not very clear. But it's actually not even substantial that the determinantal formula arises. The only thing I need, actually, when I'm doing that, is that when I'm taking generating function of these integrals, see, there is an unpleasant thing in these integrals. The contours here are nested. They're separated from each other. So if I take a very high k, these contours will blow up, right? They will be too stretched because they're different by a factor of q from each other. So if in this formula you manage somehow to shrink all these contours to a small contour near 1, you're in much better shape. And it's completely not obvious you can do that, because when you are doing that, you will have to take residues of this factor in the denominator. A remarkable fact is that one can do that, and the formula one gets is nice. And that's actually the right-hand side here. This argument, even though it might look like a miracle here, turns out to be exactly parallel to a very well-known argument, the so-called shift contour argument, that is used in harmonic analysis on Riemannian symmetric spaces. It goes back to Helgason, and this is essentially a variant of it done for Hecke algebra. So even though the transformation looks remarkable and strange and why it should be there, in the end it is there because we're working in this representation theoretic framework that makes things nice. All right, so I need to wrap up. Let me try to summarize. Okay. Now, what I tried to show first was that if you manage to start with an interesting probabilistic problem and find some solvable structure in it, or Schur functions, or some sort of algebra in it, then it's extremely helpful. You can essentially solve the probabilistic problem completely. You can usually get much more than what probabilistic methods allow. And that has been employed for a class of problems, last passage percolation problems with specific weights, exclusion processes, things like that, starting from roughly 15 years ago with great success, although the reason why these problems end up being solvable was unclear. And what I tried to explain is that if you do the reverse engineering, and rather than starting from a probabilistic problem you want to solve, you start with an algebraic mechanism that you hope will help you solve the problem, and then look for the problem. So then in the Schur case, in the Schur processes case, it works quite well. Not only one rediscovers the exclusion processes that were known to be solvable, but one comes to a much broader object, which is a two-dimensional dynamics, and actually families of two-dimensional dynamics, which I hope some of you have seen in Vadim's presentation yesterday. These are Markov chains on various types of plane partitions, on domino tilings, and on things like that. Okay? Now, after that realization comes, it turns out that what you need from the algebraic structure from the Schur processes, or from the Schur functions, is actually not just present in the Schur functions. The Cauchy identity, which is the form, some explicit form for the representing kernel in the Hilbert space, that exists in other situations. These Q-Schur functions also exist in other situations because they're just a trace of the coproduct operation in the algebra of symmetric functions. And so the object that we tried to pursue, and we had some hints that it should be useful, but not too many hints actually, were the MacDonald polynomials. They're more general than Schur polynomials, but on the surface, they had all the attributes one needed to start the formalism. Right? It didn't completely work in the sense that for the general MacDonald processes, when both Q and T general, I can't tell you what probabilistic model, I mean, I can tell you what the probabilistic model is, but it's not likely probabilists will be very interested because the interactions in the dynamics are global. Okay? It may still be that there is something there, I just don't know. We haven't had enough time. However, MacDonald polynomials and MacDonald processes, for that matter, degenerate as the parameters go to certain limits to other things. For example, they degenerate to random matrix models with general beta parameter, the ones that arise with the Vandermonde to the power beta. We don't know yet what the approach will produce there. This, what I was explaining, I mean, the other degeneration is into whole Littlewood situation, which also remains unexplored. The situation that I described here is the degeneration into the Q-Whittaker situation when the parameter t goes to 0. And that led to a fairly meaningful probabilistic model that eventually converged to this Q evolution on triangular tableaus, on triangular patterns, and later to the polymers, which people were interested in independently. And the trick worked in the sense that once we arrive there, from the algebraic perspective, the amount of tools we have for analysis is just much broader. And that ends up in actually solving the question of the asymptotic behavior. Now, what my hope is, and that's partly the reason I'm talking here, is that there are other situations in which the same mechanism of discovery somehow of interesting probability starting from representation theoretic structure, we haven't exhausted it. There are plenty of opportunities here. And maybe some of you will venture into trying to see something, trying to discover something. I'm having fun doing that, and maybe some of you will too. Thank you very much for listening.
Questions?
Alexei, have you some, don't know, more general or old conception of what does it mean solvability or integrability in probabilistic or algebraic terms? Or there are no such a new understanding with comparison with usual integrability of integrable system, not fixed.
Now, the integrability and probability that I'm talking about is different from the integrability of integrable systems. So the integrable systems are present here. For example, these commuting Macdonald operators for which Macdonald polynomials are eigenfunctions. This is a commuting family of difference operators. They form an integrable system called Macdonald-Rezonar system. But the probabilistic system I'm talking about is not that. So here is one easy distinction. All the integrable systems in analysis are one-dimensional. They are one space dimension. The growth model that I present is a two-dimensional model in space. It's a different object. It is obtained by stitching one-dimensional things, but I don't, well, for now at least, I don't know if it has a parallel in the integrable system worlds. The deeper similarity that I see, and that's what I tried to emphasize in the first lecture, is that both come as shadows of representation theoretic structure. There is some sort of an infinite dimensional representation theoretic structure, which if you project nicely, will give you either a classical integrable system, something like KdV, if you start with GL infinity, or if you project it, well, as I tried to show you, it will produce an integrable probabilistic model. But I don't, so these are sort of brothers in this sense, but I don't think that they're twins. That I don't believe. Yeah.
So to be sure, exactly which two-dimensional space you mean now?
So the triangular array that I'm talking about also has a representation as a tiling of a half plane, which can be viewed as a surface in 3D. So I'm in two space dimensions. I'm looking at the height function in two space dimensions, and I have time. There is an evolution of this random surface, and this is an integrable two-dimensional growth model that I'm talking about.
So beta ansatz has no real application to your question?
Beta ansatz may be used. So in this particular, in fact, this argument here, the replica trick, was used on beta ansatz. The reason that the physicists were able to compute this expectation was because of beta ansatz. But somehow it comes short to answer the probabilistic question. In order to get access to that object, one needs to go one level higher to the Q situation, and maybe there is also beta ansatz there, but it hasn't been worked out. Actually, there are traces of that. This is related to Q bosons, and there are papers that deal with beta ansatz, but certainly not to the level of detail that one can just take and apply there. So beta ansatz may have its place but in the approach that I described, it plays no role. It actually can be sort of extracted. You know, when one takes this integral representation and shrinks the contours, the terms that appear, they correspond to different beta states. So it's hiding somewhere, but it's not. Maybe a point that I should make is that there is no ansatz that I'm using. There are no ad hoc steps in the construction that I presented. Beta ansatz is some sort of an ad hoc construction. It's an ansatz. You're looking for something in a specific form. And what I like about the path that I tried to present is that there are no ad hoc steps. You're just sort of following the flow, and well, with some luck, you reach something in the end.
Yes, the crystallized simulation.
Oh yeah, well, but you should come up. So I stopped it. You should come here. It's on the screen, so everybody. Well, maybe you can. Well, it will take time. I think you can just pass by and see it on the screen. I don't want to close the windows for that now. Right.
So another question.
What is the kernel K of this?
What is the kernel K? That's a very good question. That's what will come out if you shrink these contours all to 1 and take care of the residues. It's explicit. You can take, the shortest way to see it is to take our paper with Corwin and look at the formula there. It's not hard, but I don't want to put it on the board now. It's explicit enough so that one can do the steepest descent analysis the way I've done on the Schur process to extract Tracy-Whittem from it. So that's actually the path that the Tracy-Whittem is proved for the polymers. One takes this kernel, does something very similar to the contour deformation argument 2 that I did 2 days ago, and that gives Tracy-Whittem. Thank you.